Hello, this is Ricky Rude. This video is a segment from a seminar given at the NOAA lab in Boulder, Colorado on December 6, 2023. The title is A Strategic Approach to Climate Modeling for Environmental Security. The full video has been split into 6 segments. Of course, the context and continuity suffer from being split up, but our attention spans are short. The full lecture and the segments are available on my OpenClimate YouTube channel, or for me, search for Climate Modeling and Environmental Security. This is Section 6, a modeling strategy proposal and concluding remarks. Thank you for listening. In many cases, it is easy to point out what is deficient in an existing practice. It is difficult to pose something that is better, much less right. To address our needs for environmental modeling, the issues are far larger than simply building models and running them. There are measurements, experiments, campaigns, and complementary research that establish the models as robust scientific tools. There are institutional resources, protocols, and practices that encapsulate such an effort. The entirety of the system will not be outlined here. The focus will be on the modeling. In all cases, it is recognized that we are not talking about just one model or the model. We are discussing a set of models that is used to investigate a specific problem. This will be referred to as the model set. First, the model set needs to be built for purpose of an application. This requires knowing the application and its inquiry well enough to develop an evaluation path that is relevant to the application and that can determine fit for purpose. It requires knowing the application well enough to describe the structural elements of models that describe the essential physics, chemistry, and biology. Simulation suites need to be designed within the evaluation plans. Second, the number of model sets and modeling institution needs to be small and focused. At some size, the logistics of the multi-model ensemble are too slowing for the urgency of the applications. The number of models needs to be decided on a scientific and resource basis. There needs to be a focus on process-based development of a small number of excellent models. Third, the model set needs to exist in a software framework and development environment that supports controlled experimentation. As this is a multi-scale problem, the requirement for interpretation at the interfaces between the scales needs to be designed into the framework and to be as robust as possible. The models need to be well documented and on defined, described, and transparent development paths. Fourth, the model set needs to serve both operations and research. The models need to have an operational predictive part of their mission. The models need to support hands-on configuration, modification, simulation design, and implementation by application experts. I note that nothing in these 4 points is new. We have fragmented capacity that should serve as an excellent foundation. It is a choice of whether we use that or decide to reinvent. I will start with the figure from above when I described weather forecasting. At this point, the figure is used only to establish that the model set provides guidance in a research process that includes measurements, experiments, campaigns, and complementary research. The figure is also used to establish a notional proposal of what comprises a model set. The notional model set includes an ecosystem of models of different scales and purpose. These include global, regional, phenomenological, process, impact, and post-processing and tailoring. One of the most important considerations in development of a strategy is to think about the important spans of time and a notional workflow from a use case. Here I will use adaptation because, for me, it is more well known than notional. If we consider time spans on which we plan, we find many important decisions of public, private, and individual investments are on decadal time spans. If we look at typical projects, they include planning, design and engineering, permitting, implementation, and use. We pose here a 50-year use time. At this point, the climate is changing significantly on a decadal time span, and the evidence suggests this will remain true for all reasonable planning and implementation horizons. We will be in a state of constant monitoring and replanning. Currently, CMIP, analysis, and model use evolved on a half-decadal to decadal time span. The urgency to address these problems and the non-stationarity of climate require us to decouple adaptation, geoengineering, examination of tipping points, and many other problems from CMIP. We need a routine operational capacity producing simulations on decadal time spans. Next, I want to modify the notional model set. I will focus on a couple of items that I think are most deficient. I first alter and expand the global model type. It is essential that we move away from our high reliance on ad hoc ensembles and ensembles of opportunity. The roles of ensembles in prediction are so important that we need to elevate science-based, purpose-based design. We do need to maintain CMIP and CMIP-type approaches. The strengths of CMIP-type approaches are too many to enumerate here. The CMIP archive is often the first database of exploration and interrogation. Given the human, monetary, and computational resources required, the CMIP-type simulations need to be appropriately sized to the model set as a whole. We need global predictive models with focus on a 10 to 50-year event horizon. This is a time span that has traditionally been not only ignored because of perceived predictive challenges, but dismissed. I assert that at least part of this dismissal is because of the bias in our community to view problems from an atmospheric and weather perspective. Experience shows that if we actually focus on a problem, then we better examine the physics and the processes. Of critical importance is better inclusion of the oceans and interactions of the ocean with the atmosphere. Important aspects of this focus include the monitoring and understanding of the warming, sea level rise, changes in regimes of precipitation and evaporation, ecosystem changes, compound events, adaptation, geoengineering, and effectiveness of mitigation policy. Of primary importance is the reduction of bias in key variables. The atmospheric model needs to focus on process, the attributes of weather, namely the role weather plays in the transport of moisture, heat, and momentum. Attention needs to be paid to teleconnections, for example El Niño, and not only the ability to simulate teleconnections, but their relationship to weather features. The design and implementation of the model should presume its interfaces with other models in the model set. I next expand on the regional model types. Regional models have many advantages, including the ability that meaningful simulations can be run on widely available computational platforms. They provide a way to scale across applications and, more importantly, across expertise, training, and local knowledge. Regional models are unlikely to correct the errors, especially the bias errors of global models. Indeed, they will inherit those errors. Therefore, attention needs to be placed on the interfaces, including the development of standard protocols and training to assure that practitioners understand how global models influence regional models. As with global models, it is essential that we move away from our high reliance on ad hoc ensembles and ensembles of opportunity. The roles of ensembles in prediction are so important that we need to elevate science-based, purpose-based design. We need to integrate weather forecasting techniques into the model set. Climate is often defined as the average of weather. It is also useful to think that our climate depends on the cumulative transport effects of weather systems. Furthermore, weather is the way we feel the consequences of a changing climate. Weather is important to the practitioners and the need for local knowledge. The ability to have a weather forecasting capability in the modeling set offers strategies to investigate transport in case studies and use cases, investigate the interchange of energy, momentum, and moisture at surfaces, attribution, and a strategy to manage bias in adaptation applications. This is important for adaptation as initial and boundary conditions that are modified to represent changed climate backgrounds can be used to investigate how storms that have revealed vulnerabilities are modified. It is a way to provide quantitative local information for planning that cannot be derived from global or even regional climate simulations. Such techniques can better manage the biases of global and regional simulations. Ensembles with hundreds of members can be used to explore, for example, a proxy Hurricane Hugo's effects on Charleston, South Carolina. This is a place where methods based on machine learning might be strong contributors. The other types of models, phenomenological models, impact models, process models, and post-processing and tailoring, offer high flexibility, and efforts should be made to integrate them into the model set. I hope I have presented a cogent and convincing presentation that conveys that we are on a path where we have an unprecedented need for model-based science to help guide us into the rapidly changing climate that we have created. I have tried to frame this as our existing models, most notably those associated with the Coupled Model Intercomparison Project CMIP, have been uniquely successful in providing us with a credible but fuzzy vision of our climate future. We need to develop new approaches to model design and simulation design to provide us tools to clarify that vision. We are sitting at the edge of a climate wilderness, which is both familiar and alien. Models are what we have to help navigate us through that wilderness. I have demonstrated why CMIP and CMIP-like approaches are not sufficient to provide the guidance we need to manage monitoring, non-stationarity, uncertainty, and provide a credible representation of weather. We need better models to inform decision-making for tipping points, managing emissions, is policy working, geoengineering. The list goes on. I have posed some organizing principles for model sets to better provide needed information. These include the fact that models are built and evaluated for purpose, and the primary role of models is to provide guidance in concert with other knowledge to support expert guidance that informs decision-making. It is both sound scientific and ethical practice to derive decision-relevant knowledge from models suitable for purpose. I realize that nothing I propose here is uniquely new. I am also aware that there is an emergent sense in our community that we need new approaches to modeling. Most of what I have seen, however, is anchored around making what we have done bigger and better. What I present here is more connected, and I pose as more strategic. I have been asked, what do I want people to take away from this talk? I think first, if you're in a position of influence, especially in the U.S. government, what we have been doing regarding modeling and modeling policy is not sufficient, adequate, or fit to the purposes of the decisions that we will need to make. There is need for an authoritative, trusted source of model guidance. We can continue to leverage or reframe our current capabilities, but it takes an excessive amount of time, and the outcomes of the effort are difficult to defend. We can continue to fund and manage models as we have, which is minimally inefficient, arguably ineffective, and I assert will become less competitive with other nations. We need to do something different than continuing to do what we know how to do. This is difficult culture change. If you are a scientist or a practitioner who needs model guidance for your work, then you need to develop strategies and skills to extract what you need from our current model knowledge. The good news is that there is, in general, usable and defensible information available. There are strategies that involve developing scenarios and model-informed plausible storylines to manage uncertainty. What I suggest here that we need to explore are evolving techniques that better link predictive science and weather modeling to climate knowledge. This is a strategy to provide quantitative information for planning, design, and engineering. The lack of model guidance, however, is not the most important missing knowledge in addressing climate change. It is knowing how to apply what we have to our real-world problems. This will always be the case. Thank you for listening.